Hey everybody, Trey here. Welcome back to another episode of this video series on Skew-Ts and Hodographs. In our last video, we started to discuss a bunch of these different environmental parameters that we can find using a Skew-T, and we actually calculated some of them and showed you how to calculate them. We got through quite a few, but there's quite a few left, so we're going to get right into it here in this video. We left off by looking at the convective condensation level, the convective temperature, and the maximum temperature, and how you find those from the sounding. We will start off today by looking at a pretty simple parameter, but it does have some importance when we're talking about the potential for large hail or the precipitation type near the surface in winter weather scenarios, and that is the freezing level. And the freezing level is basically exactly what it sounds like. It's abbreviated FRZ, or I've seen it as FZL on the SPC soundings, but the freezing level is basically the level where the 0-degree isotherm matches or intersects with the environmental temperature profile. So all we do is we find our 0-degree isotherm here, which is going to be this guy. We go all the way up, and wherever that intersects with the environmental temperature profile is our freezing level. So in this case, it's going to be just above 600 millibars, probably something like 580 millibars. So again, very easy to find. It can be given in both millibars as a pressure level or in feet. You'll see on the SPC soundings that it's given in feet above ground level. And really the times we use freezing level is number one in severe weather scenarios when we're looking at the potential for large hail. If the freezing level is lower to the ground, that means that hailstones have a lot more time in the updraft to grow and a lot less time to melt before they fall out of the updraft and hit the surface. So when the freezing level is lower, the potential for large hail increases. And we also use the freezing level in winter weather scenarios. If the freezing level, the closer the freezing level is to the surface, the more likely that frozen precipitation is going to fall at the surface. So if you're in a winter weather situation and the freezing level is quite near the surface, once again, that frozen precipitation aloft is not going to have much time to melt before it hits the surface. So therefore, you're going to see some form of frozen precipitation at the surface, such as snow or freezing rain, when that freezing level is closer to the surface. So we will go ahead and log our freezing level here as about 580 millibars. All right, the next variable we're going to discuss is one that's not really used a whole lot, but it is used to determine some of the parameters we're going to talk about here shortly, and that is the wet bulb temperature, abbreviated as T sub W or T sub WB. And the wet bulb temperature is basically the temperature to which a parcel of air at a constant pressure cools through the evaporation of water into it. So generally the wet bulb temperature is measured on this thermometer. It's got a little sort of Q-tip looking thing on the end of it, which is the bulb, and it's wrapped in this wet sort of fabric. And the temperature that the bulb will cool to, based on the evaporation of the moisture on the bulb, is the wet bulb temperature. Now it corresponds, it's important because it takes into account both kind of the temperature and the moisture content in the atmosphere. So let's kind of do this analogy here to kind of help you understand what the wet bulb temperature shows. Let's say you are in the middle of the southern plains in the summer, where the air is really, really juicy, it's really, really moist. And let's say you do some vigorous exercise outside, and you're sweating quite a bit. Well, you'll notice that your sweat does not really evaporate off you that well, because there's so much moisture already in the atmosphere. Now, let's say you do that same thing in, let's say, the winter in Arizona, where the air is really, really dry. Well, your sweat is going to evaporate pretty quickly off you because the air is so dry that evaporation is a lot more favored. So that's what the wet bulb temperature does. If the wet bulb temperature is fairly close to the actual temperature, that means your air is really, really moist, and that evaporation is really not that present because there's so much moisture in the air. But if your wet bulb temperature is a lot less than the actual air temperature, which means the bulb has cooled a lot via a lot of evaporation. That means the air is really dry, and evaporation is more favored. So that's all the wet bulb temperature does. It's, again, not really used super often, but the way you find it on a sounding is you first find the LCL at a certain pressure level. You can do this from the surface. You can do this at 850 millibars, whatever you want. So, and then after that, you follow the moist adiabat back down to the original pressure level. So let's say we wanted to find the wet bulb temperature at the surface. So what we would do, we'd first find our LCL by going up the dry adiabat from the temperature at the surface, going up the moist adiabat from the dew point, and we find our LCL, which, as we found earlier, is about 860 millibars. Then from there, we'd follow the moist adiabat, which again are these curved dashed green lines here. We'd follow that back down to the original pressure level. So we go back down here and plot our value, and the wet bulb temperature at the surface would be, let's say, so here's our 20 degree isotherm. Here's 30, so it's pretty close to 20. I would say that's probably 22 degrees Celsius. Now let's say we wanted to find the wet bulb temperature at, let's say, 850 millibars. So what we would do is we'd find the LCL at, let's say, 800 millibars, just to make it a little easier on us, because we actually have an 800 millibar isobar here. So let's say we wanted to find the wet bulb temperature at 800 millibars. Actually, this will be easier. So what we do, we'd find the LCL at 800 millibars. So we'd start at our temperature at 800 millibars. We'd go up along the dry adiabat. And then we'd follow from the dew point at 800 millibars. We'd follow our mixing ratio line upward until the two intersect, which would be right about that point. And then we would bring our parcel down along the moist adiabat, so parallel the moist adiabat, all the way back down to 800 millibars. And that would be your wet bulb temperature, which in this case is a lot closer to the 10 degrees Celsius isotherm than it is to 20. So I'd probably say something like 12 degrees Celsius. So that's how you find the wet bulb temperature. Again, it's not super complicated, not really used that often, but actually the SPC, if you look on SPC soundings, they actually plot the wet bulb temperature profile. It's going to be this blue line, this blue profile right here. So they do some calculations based on the environmental temperature. They do that process that we went through and actually plot it for every single point up as you go up in the atmosphere. So that's the wet bulb temperature. For our purposes, let's go ahead and just plot the wet bulb temperature at the surface. We said it was about 22 degrees Celsius. So that's how you find the wet bulb temperature. Now, from the wet bulb temperature profile, we can find something called the wet bulb zero level. And I'm going to move this up just a little bit so I have a little bit more space to write here. But we can now find something called the wet bulb zero level, or WBZ. And this is pretty much the exact same thing as the freezing level that we talked about a few minutes ago. And it's basically the lowest pressure level where the wet bulb temperature is 0 degrees Celsius. So all you do to find that is go to our wet bulb temperature profile. Remember, it's the blue line right here. And we just follow the 0 degree isotherm up until it intersects with this wet bulb temperature profile. So we'll go up along the 0 degree isotherm here, all the way up, right where it intersects the wet bulb temperature profile, which in this case, which this is the same sounding that we've been looking at here for all of our parameters, would be something like, this would be 550, 600, 650. So actually right about 600 millibars is our wet bulb zero level. So let's go ahead and plot that on our chart, wet bulb 0 level equals 600 millibars. And the wet bulb 0 level pretty much has the same significance as the freezing level. It's just a level where the lowest wet bulb temperature is 0 degrees Celsius. So the closer that the wet bulb 0 temperature is to the surface, the more likely that you are to have large hail, because again, the hailstones have more time to grow within the updraft and less time to melt before they reach the surface as they fall out of the updraft. And number two, the closer the wet bulb 0 level is to the surface, the more likely you are to see frozen precipitation at the surface, because again, those frozen precipitation particles are less able to melt with the freezing level or the wet bulb 0 level so low near the surface. And one more quick thing about the wet bulb 0 level is that it can be given in feet as well as in millibars. The SPC soundings will give it in feet. We did it in millibars for simplicity's sake. Now we're going to talk about several different temperature variables that incorporate moisture. And these can be sometimes more useful than looking at just the temperature or just the dew point when assessing the temperature and moisture content of the atmosphere, respectively. A few of these are more important than some of the other ones, and I'll tell you which ones they are when we get to them. But we're going to start with one that is called virtual temperature. And virtual temperature, abbreviated as T sub V, is the temperature at which a parcel of dry air would have the same density as a parcel of moist air at a constant pressure. So let's say we have two different parcels here, parcel 1 and parcel 2, and let's say their temperatures are the same. Let's say they are both 20 degrees Celsius. But let's say parcel 1 is dry, it has no moisture in it, and that parcel 2 is full of moisture, full of water vapor. Now, a couple of things to know before we get into this discussion, and that is that water vapor is less dense than dry air. So when you have a moist parcel, it is going to be a lot less dense than dry air because water vapor itself has less mass than the typical constituents of the atmosphere, nitrogen, oxygen, etc. And we know that warmer air is less dense than colder air. And that's basic just physics. We know that warm air rises and cold air sinks. Well, it's because cold air tends to be more dense than warmer air. So back to our parcels here. Parcel number 1 is our dry parcel. Parcel number 2 is our moist parcel. So parcel number 2 is going to be less dense than parcel number 1. Well, how do we make them the same? Well, we can do one thing, and that's heat up parcel number 1, because we know that warm air is less dense than cold air. So we can heat this up to make the densities match up. And the temperature that we need to heat parcel number 1 to in order for the densities to match, that is the virtual temperature. So if the virtual temperatures are the same between parcel 1 and parcel 2, we know that they are the exact same density regardless of how much moisture content is in each individual parcel. So I hope that makes sense. That's the virtual temperature. And the virtual temperature is always going to be greater than or equal to the actual air temperature. And once again, it accounts for how the moisture content of a parcel changes the density of that parcel. So the way we find the virtual temperature from a sounding is we first find the mixing ratio passing through the dew point at a given level, and then we use this equation, that virtual temperature equals the temperature at a given level plus the quotient of the mixing ratio divided by 6. So from that, we know that the mixing ratio is always positive, so that the virtual temperature always has to be greater than or equal to the actual air temperature. So I'm going to clear the screen here so we have a little bit of room to work. Let's find the virtual temperature at 800 millibars. So we can find the virtual temperature at any level of the atmosphere. I'm going to pick 800 millibars here just as an example, and because we have a nice mixing ratio line to correspond with the dew point at this level. So we first find the mixing ratio corresponding with the dew point at a given level at 800 millibars. So that would be right here. So there's where the dew point line crosses the 800 millibar isobar. And here's our mixing ratio line. We see that this is the mixing ratio line here going through that dew point value, and that is going to be 8 grams per kilogram. So our mixing ratio at 800 millibars is 8 grams per kilogram. So all we do is we take the temperature at 800 millibars, which is found on our environmental temperature curve. Again, we figured that out to be about 22 degrees Celsius. Here's our 20 degree isotherm, 30 degree. It's closer to the 20, so we'll say 22 degrees Celsius. So our temperature at 800 is 22 degrees Celsius. And before we continue, the virtual temperature is given in Kelvin. It's just another temperature unit. It's pretty much the same as degrees Celsius, and the way we convert between the two is to find the Kelvin value of a certain degrees Celsius temperature. We take that degrees Celsius temperature and add 273.15, or to make it a little more simple, 273. So our temperature at 800 degrees is 22 degrees Celsius. We take 22 degrees Celsius plus 273, and that gives us 295 Kelvin. So our temperature at 800 is 295 Kelvin. So all we do is we use our equation that the temperature, we take the temperature plus the mixing ratio over 6, that quotient there. So 295 Kelvin plus our mixing ratio, which is 8 grams per kilogram, over 6, which happens to be 1.33. So 295 plus 1.3 gives us a virtual temperature at 800 millibars of 296.3 Kelvin. So virtual temperature at 800 equals 296.3 Kelvin. And we can find a virtual temperature for any point on this temperature profile. We just use this equation of the temperature at a given level plus the mixing ratio at that level over 6, that quotient added to our temperature at that given level. All right, the next variable we're going to talk about is something called the equivalent temperature. And the equivalent temperature, which is abbreviated T sub E, is similar to the virtual temperature in that we don't really use it in its raw form when making a forecast. We're not going to pull up a map of equivalent temperatures and assess anything from it. But knowing how to find the equivalent temperature is critical for a variable we're going to talk about in a few minutes called the equivalent potential temperature. So you need to know how to find the equivalent temperature in order to find the equivalent potential temperature at a certain pressure level. So the equivalent temperature is basically the temperature that a parcel of air at a certain pressure level would have if all of its moisture were condensed out by a pseudo-adiabatic process. So in simpler terms, you're just taking a parcel, you're squeezing all the moisture out through condensation, and when that happens, the latent heat of condensation itself heats the air and heats the air parcel. So because of that, the equivalent temperature is always going to be greater than or equal to the actual air temperature. And the way we find the equivalent temperature is we first find the LCL at a given pressure level. We squeeze all the moisture out. So we take the parcel up to a level where the moist adiabat parallels the dry adiabat. Because at that point, when the dry adiabats parallel the moist adiabats, the parcel no longer has much moisture in it at all, so it's rising at the dry adiabatic lapse rate. And then when we take it up high in the atmosphere, to that point, we follow the dry adiabat back down to the original pressure level. So, for example, let's find the equivalent temperature at, let's say, 600 millibars. So first we find the LCL. So here's 600 millibars. Of course, we follow the dry adiabat up from the temperature line, and we follow the mixing ratio line up from the dew point until the intersection point of those two. And now we're going to follow the moist adiabat up. We're basically going to draw a parcel trace here. So we're going to follow the moist adiabat up to a point where the dry adiabats parallel the moist adiabats. So often that's something like 200 millibars. It's not that critical to pick a level to bring the parcel up to when you're finding the equivalent temperature. Just go to somewhere where the moist adiabats are somewhat parallel to the dry adiabats. I like to go up to about 200 millibars. You can go up higher. It's really not that much difference. Even 300 millibars is often adequate, but I like to go up to 200 millibars. And then what we're going to do is we're going to bring the parcel all the way back down along the dry adiabat back to the original pressure level. So we're going to follow the dry adiabat all the way back to 600 millibars. And the temperature, after we do that, is the equivalent temperature. So right about there. Of course, it's a little off because drawing on this annotation tool is a little bit difficult. But we'll estimate it as something right about there. So the temperature at this point, when we've descended the parcel all the way back to 600 millibars, that is your virtual temperature. So right here, it's kind of closer to the 22 degree line than the 20 degree line than the 30 degree isotherm. So we'll say that the equivalent temperature at 600 millibars is about 23 degrees Celsius. So that's how you find the equivalent temperature. It's, again, not super important in its raw form for forecasting, but we do need to know how to do it in order to find the equivalent potential temperature, which is a variable that's critical when we're forecasting severe weather. All right, now let's find something called the potential temperature. And the potential temperature is symbolized by the Greek letter theta. And it's simply the temperature that a parcel of air would have if it were brought dry adiabatically down to a pressure level of 1,000 millibars. So normally we can't really compare the temperature or the energy of a parcel at 1,000 millibars to the energy of a parcel, say, at 500 millibars, because temperature decreases with height in the atmosphere. So a parcel naturally that's at 500 millibars is going to be a lot colder than it is at a parcel at 1,000 millibars. But using the potential temperature, we can standardize all the temperatures by bringing them all back to 1,000 millibars, and thus we can then compare parcels, the energy of parcels, at different elevations. And because potential temperature is conserved during lifting and sinking, the potential temperature of a parcel, if it's lifted to 500 millibars, it's going to be the same as it was at the level that it was lifted from. So all you do to find the potential temperature, whose units are, again, in Kelvin, the potential temperature is simply you take the temperature at a given pressure level and you follow the dry adiabat all the way back down to 1,000 millibars. So, for example, let's find the potential temperature at 800 millibars here. So all we do is find the temperature at 800 millibars, follow the dry adiabat all the way back down to 1,000 millibars, and the temperature at that point is going to be your potential temperature. So right about here is going to be that point just to the right of the 40 degree isotherm, so we'll say 41 degrees Celsius. And of course, converting to Kelvin, 41 degrees Celsius plus 273 equals a potential temperature at 800 millibars of 314 Kelvin. So that's all the potential temperature is. It's a way of standardizing the temperatures and allowing us to compare the energy of parcels at different elevations. So one thing to remember when you're looking at these variables, and you maybe see a variable that you don't remember, whenever you see the word equivalent, and I'll change colors here for this, whenever you see the word equivalent, it means get all the water out. So all that means is take the parcel up to a level in the atmosphere where the dry adiabats parallel the moist adiabats, like we did for the equivalent temperature. And whenever you see the word potential, it means bring down to 1,000 millibars. So we would just do what we did here and take the parcel and just descend it along the dry adiabat down to 1,000 millibars. So that kind of leads into our next variable. Let me clear this off here. which is going to be called equivalent potential temperature, or as it is kind of more commonly known and abbreviated as theta-e, theta sub e. And the equivalent potential temperature is what it sounds like based on what we just said. It's the temperature at a certain pressure level that a parcel of air would have if, one, all of its moisture were condensed out by a pseudo-adiabatic process, i.e. squeezing all the moisture out, which is the equivalent part, and then brought back dry adiabatically to 1,000 millibars, which is the potential part. So we're basically just combining the equivalent temperature and the potential temperature here. So let's find the theta-e at 600 millibars. So once again, we'll find the LCL at 600 millibars. We will follow the moist adiabat, up all the way to a level where the dry adiabats parallel the moist adiabats, which is about right there. And then now we'll bring it, instead of bringing it back down just to 600 millibars, we're going to bring it all the way back down to 1,000 millibars, which is the potential part of this. So we'll follow the dry adiabat back down, and it looks like this is going to go off the chart a little bit, but we can kind of extrapolate here. So now we brought it kind of back down to 1,000 millibars. We'll extend that over a little bit. That's 1,000 millibars. So the temperature at this point is your equivalent potential temperature. So here's our 40 Celsius isotherm. The 50 would be right about there, and probably the 60 would be right about there. So the equivalent potential temperature of this would, let's say it would be about 62 degrees Celsius. And of course, the equivalent potential temperature is given in Kelvin. So 62 plus 273 equals 335 Kelvin. So our equivalent potential temperature at 600 millibars would be 335 Kelvin. And the equivalent potential temperature, or theta-e, is important for severe weather forecasting because it helps us assess the areas of highest sort of potential instability. In other words, it's where the juiciest air is. The higher the value of theta-e, the more juicy the air, because theta-e takes into account temperature and moisture. So it basically tells us, where is the most energetic air. So, and we use that in severe weather forecasting a lot because unlike the temperature and unlike the dew point, this theta-e combines kind of both of those temperature and moisture aspects. So wherever theta-e increases, that means you have an increase in temperature, increase in moisture as well in those parcels in that area. So that's what equivalent potential temperature is. Let's go to our last sort of variable here before we get into stability indices, and probably going to stop here for the sake of not making this video too long. But our final sort of temperature thermodynamic variable is our wet bulb potential temperature, or theta-w. And basically, it's just the wet bulb temperature a sample of air would have if it were brought along a moist adiabat to a pressure of 1,000 millibars. So if you recall back to when we talked about the wet bulb temperature, all we do to find that is we find the LCL at a certain pressure level, then bring that parcel back down to the original pressure level along the moist adiabat. But instead of bringing it down to the original pressure level, again, we see potential here, so we're going to bring it down to 1,000 millibars along the moist adiabat. The theta-w, not really used that often, not super important, but just wanted to show you how to do it in case you ever need to know what the wet bulb potential temperature is. So let's find the theta-w at 800 millibars. So all we do is we find the LCL. Of course, we've done this a few times here at 800 millibars. We follow the dry adiabat up, follow the mixing ratio up from the dew point, where those two intersect is the LCL. Then we bring it back down to 1,000 millibars along the moist adiabat. So we're going to parallel the moist adiabat all the way back down to 1,000 millibars. And the temperature at that point is your theta-w. So it looks like it's right on the 20 degree isotherm. So nice and easy, 20 degrees Celsius converting to Kelvin, 20 degrees Celsius plus 273 equals 293 Kelvin. Theta W at 800 millibars. Again, not used that often. Equivalent potential temperature is used a lot more often, as it's probably the most widely used of these variables that we've talked about in this video in terms of the temperature variables, at least in forecasting severe weather. So with that, we'll stop there. And in our next video, which will be the last in sort of this mini series within the bigger series on the how to calculate these parameters from a Skew-T, we'll take a look at different stability indices. So things like lifted index, the K index, etc. Basically, ways we can determine the sort of likelihood of thunderstorms or severe thunderstorms from just a basic sort of composite parameter we can find from the Skew-T itself. So hope you've learned something from this. Thanks for watching, and we'll see you in the next video.